Good morning, everyone. Welcome to the Easy Power Tuesday Refresher Series. My name is Jim Chastain. I'm with the Applications Group here at EasyPower. Today, the topic is using EasyPower PowerProtector to coordinate ground systems. Very much appreciate your attendance today. What we'll be talking about is first kind of a grounding background, a real brief introduction, the type of ground systems that require coordination. And basically, we're going to show an example of high resistance grounded and then hard grounded. And I just want to mention this is not meant to be an exhaustive examination of the topic whatsoever. Basically, we're trying to demonstrate the use of the tools and identify the functions of the protective devices and ensure that they're coordinated. We will have a more advanced discussion on the topic in a future date. So I appreciate your patience. So traditionally, there were really only two choices as far as grounding, and that in the early days of electricity, a hard grounded system basically improved safety from ground fault electroshock, and that any fault went directly to ground, and it was easy to detect a ground fault. Unfortunately, it brought things down pretty quickly when that happens. And it could cause high ground current, which could easily migrate or elevate to an arc flash incident. And then it does need coordination because you don't want a very remote fault pulling down the whole system. And then the other alternative was an ungrounded system. And here are the limits of having a ground fault would not be detected, and consequently it increased our uptime of our system. And the idea was to make repairs during system shutdown so we didn't have to worry about the system being pulled down as frequently as initial minor fault repair would require. Trouble is, when you had multiple faults like this, it's difficult to locate the low current faults. And if you have a system that tolerates a number of low-level ground current flows, you have the potential for, over the long term, having deterioration of your insulation, which has other issues and can result in things like arcing faults, in addition to hard faults down the road. And then in the 1980s, the system of high resistance grounding came into vogue, and in part because it limited the amount of ground current and the electroshock potential in the system, and it allows the system to stay up with multiple grounds. The downside was, again, if we have the ability to tolerate multiple grounds, it wasn't always easy to locate each and every one, and for certain, it does require coordination for best results. So that's kind of where we stand today between the two options. And rather than an ungrounded system, more than likely you still find a lot of ungrounded systems. And some of the discussion is aimed towards conversion, and I'll leave kind of that discussion up to the design committees. What we're going to talk about today is various functions and their application at different parts of the system. And specifically, these are some ANSI codes for relay functions that are used for grounding. 51G is a time over current for ground. 51N is neutral time over current. And then instantaneous is a 50G or a 50N. And CTs are selected when you have a high resistance ground. They need to be selected for the ampacity range of the resistance that you've used in the system. And so what we're going to look at in EasyPower, as I indicated, were a couple examples The upper half of this diagram is high resistance grounding. In this case, we've selected a 1200 amp resistor, ground resistor, and that allows us a lot more tolerance to ground current. And then the lower half will be a hard grounded system. So a typical resistor grounding system has basically multiple levels or zones of tolerance or overlapping protection. First of all, when we're looking at our first level of protection, it basically relies on the function of the 50G relay we have at the bottom, in this case detecting through a zero sequence CT, and its sensitivity can be gauged based upon what we want to tolerate as far as a continuous low-level ground. And the second level of protection is provided by the 51N function, which we'll see is initially picks up at 25% of the ampacity rating of our ground system, and then we want to coordinate it with the feeder relays below. And then thirdly, we'll utilize as our last level line of defense the ground in the current in the ground leg going to the high resistance at the transformer. And this again is rated, we want it to at least sense the current to start to pick up at 25% of the rating, and we want it to be coordinated with the elements below it. So let's jump into EasyPower and see how this works. So if I'm in the database edit, and we're going to look at the setup of this 50G relay, and the part we've just kind of selected out of the air is a GE part, multifunction, and one of the functions is a 51G capability. And so we've got it connected to the medium voltage breaker that's supplied to the rest of our system downstream. As far as settings, again, we're going to set it at a relatively low level, and the sensitivity on the dial, or how long we'll tolerate that level of current, is a decision we make at the time we build the system. Most of the time, the relay at this part of the, or at this level of protection, we really don't want to have instantaneous response. So let's see how this looks in the PowerProtector TCC display. All right, first of all, above everything else, before we can display the performance of this particular relay, we have to generate a line to ground fault. So that can be either a single line or a dual line, in which case the tool has the ability, well, let's do that again. The tool has the ability to show the presence of that fault, or it won't if we're doing a balanced fault with no line to ground fault. So let's try this again. Expand it a little bit in our block diagram. So what we've done is set up the pickup point is this tick mark up at the top of the screen. And you can see we've set it up here for 10 amps, or a 10 amp range, and then it's scaled based upon where we set that tap. So if we set it higher, meaning we'll tolerate current at a higher level at this point, at this point I've got it set to 20 amps, and then the time dial determines how long we're going to tolerate that particular level of ground current. So at this point, we don't necessarily, it depends on the building design and what our type of equipment we're using, but for the most part, this is our first level of defense, and we need to have it relatively low to coordinate with all the devices above it. So for starters, let's go ahead and set it relatively aggressive and make it responsive to something like that. Then our next level is the 51N, which is this relay up here. And if we expand that, apply a single line to ground fault. In this case, we've chosen a multi-lin 735 and a 51N ground overcurrent. And the settings here were, we want to set it at 25% of the rating. The NPR rating of the resistor is 1200 amps. So let's set this at 300. I guess I can get there. And it could be adjusted with this little tab here at the top. So let's start off with 300 and see how it coordinates with everything else. All right, likewise, the time dial is can be set after we realize what we're trying to protect. But for the most part, this is how long we're going to tolerate that particular level of current. So let's set it a little bit lower. And again, we're not, we come back and look at our settings, we're not tolerating any instantaneous trip, in part because it interferes with coordination. And then finally, when we go to the ground current in the 51G relay, I guess I didn't need to do that. Again, we want to set its pickup at 25%. And so 300. And again, this is where we would coordinate against the other devices. So let's put them all on the same graph, same plot. All right, so here's our 50G down here, ready to detect relatively low levels of zero sequence current. And again, how much we want to tolerate is the minimum point set here. To coordinate these with the same pickup rating, we need to adjust the time dial, and in essence, make them parallel as much as possible. And at this point, we see some coordination with the 51N tripping first at this level, and then the ground current sensor tripping at that level. So at this point, we've got the protection coordination verified. And if we want to determine the difference, the time difference between a particular ground fault, we would select the two curves, see the difference calculator, and this shows us our different time difference, in this case a little over 2 seconds at the closest point of approach. All right. All right, so that's a grounded system, high resistance grounding, and it's relatively straightforward. Probably the trickiest part is remembering to apply either a single line to ground or dual line to ground fault as we're doing the coordination. All right, so let's close this and go down to the hard grounded side of the fence. Here it's a little bit different. because in the solid ground, where we have basically any ground, line to ground is of concern. We have integrated fault protection in our breakers, in our low voltage power circuit breakers and our molded case circuit breakers. So the 51D, or the ground fault detection in the downstream breakers, is the minimum setting that we need to set so it can be selectively set with anything downstream. So the coordination, you want the remote breakers to trip first, and then the breakers farther upstream to trip secondly. So let's see how this looks in the most upstream device. We want to set relatively high, and then as we get farther downstream, if we're coordinating with a fuse, we may or may not set the in or out condition of the I²T setting, and then deal with the coordination between the different breakers. So let's see how EasyPower handles this. All right, so in part we're looking at transformer protection and ground coordination. So let's plot all three devices. And again, we want to primarily look at ground fault. So it's showing us the phase trips curves as well. Let's take those off the display by selecting just ground coordination. And what we see here is that we have two similar breakers with these Cutler hammer devices, and consequently they're not going to coordinate unless we modify one of the settings. So if we go in and look at this farthest downstream ground fault trip, we say that its setup is at the lowest point. If we set it higher, it would be less responsive, or it would respond at a higher current. So for the most part, we want to pick up as low as possible and as quick as possible. So the delay ranges from a tenth to a half a second. We'll go ahead and stay with the half a second. And what that tells us is the upstream one is set too low. So if we go to the upstream ground trip, we want to pick it up slightly higher, and it's already set at the longest delay. And so for coordination purposes, it would look like this. Now, even though this breaker is downstream of the main, and it's in parallel with our feeder breaker downstream, it doesn't have to coordinate with the fuse, but we may want to coordinate our upstream breaker, our upstream main, with the fuse protection downstream. So when that's the case, we can open up the fault curve or the trip curve, and for ground trip, put the I²T in, which puts this little corner protection in the curve and allows us coordination with the downstream fuse. So at that point, and this can be adjusted if we want it a little bit better separation or less, we can make these adjustments on the screen or in the setup of the breaker itself. So at this point, it looks like we have fairly good ground fault coordination between the upstream main, the downstream, and at least one of the feeder fuses. And we'd save this plot and call it good. All right, so that was kind of the short and sweet version of it. What we've learned is that probably the trickiest part of using the Power Protector module is making sure we're looking at a fault which is examining only the ground fault currents. And so we have to pick out either a single line to ground or a dual line to ground. And based upon that, we can make adjustments and coordinate the ground fault protection. both for a hard grounded and a high resistance grounded system. Appreciate your attendance today. Check the newsletter for new announcements. Those of you that may have seen an announcement here within the last week, the EasyPower 10.2 has been released, and now we have the capability of implementing or conducting studies using the new standard IEEE 1584 2018. Invites you to visit the EasyPower website from time to time and at least take note of the banner on the EasyPower start page. Once again, thanks for attending, and we'll talk to you next time. Have a good day.